Have you ever wondered why things around us move? Well, Sir Isaac Newton discovered the amazing secret. Let's discover how motion works. It's going to be an amazing journey. Ever wonder why a skateboard stays still until you push it? That's Newton's first law of motion. Isaac Newton discovered that objects like to keep doing exactly what they're already doing. Think of a rocket. It stays at rest on the launch pad because its inertia keeps it there. It needs a massive force from its engines to start moving. Once those engines fire, they provide the force needed to overcome that inertia and blast into the sky. In space, Newton's law is even clearer. Once the shuttle is moving and the engines cut off, it will keep gliding forever. Without air or friction to stop it, the shuttle stays in motion at the same speed and direction. That's inertia in action. So, objects keep doing what they're doing until a force steps in. That's inertia. Now we know that objects keep moving unless a force stops them. But what happens when we push harder? Next, let's discover how force controls motion. Why is it easier to push an empty cart than a heavy one? The answer comes from Newton's second law of motion. This law explains how force, mass, and acceleration all work together. Newton discovered that motion depends on two key things: force and mass. The stronger the force you apply, the faster an object speeds up. But the more mass an object has, the harder it is to get it moving. This relationship is captured in one of the most famous formulas in physics, F equals m times a. In simple terms, force equals mass times acceleration. Let's break down exactly what that means. First, F stands for force. A force is any push or pull. Think of it as the energy you put into an object to make it start moving, stop, or change direction. More force means more oomph. Next is M for mass. Mass is the amount of stuff inside an object. The more matter it has, the more it resists changes in its motion. That's why a bowling ball is harder to throw than a tennis ball. Finally, A stands for acceleration. This isn't just speed, it's how quickly that speed is changing. When you step on the gas in a car, that sudden surge of speed you feel, that is acceleration. Let's do a quick calculation. Imagine you have a box with a mass of 50 kilograms. If you wanted to accelerate at 2 meters per second squared, you simply multiply them. 50 times 2 equals 100. In physics, we measure force in a unit called the Newton, named after Isaac himself. So, to move that 50 kilogram box, you need exactly 100 newtons of force. It's as simple as that. We see this in nature every day. A cheetah has a relatively small mass but incredibly powerful leg muscles. This allows it to generate massive force, resulting in the fastest acceleration on land. In space, the stakes are even higher. A rocket has a colossal mass, so it needs a truly gargantuan amount of force from its engines to overcome gravity and accelerate into orbit. No force, no space travel. So remember Newton's second law, force equals mass times acceleration. Whether you're pushing a cart or launching a rocket, the math is always the same. More mass needs more force. More force brings more speed. We learned that stronger force makes objects accelerate faster, but every force also has a partner. Get ready for our next chapter, Newton's third law of motion. Let's dive into the science of action and reaction. Have you ever wondered why a skateboard rolls backward when you jump off it? It seems like it has a mind of its own, right? But this isn't magic. It's the result of one of the most fundamental laws of our universe. In fact, you use this law every time you take a step. When you walk, your foot pushes backward against the ground. Because you push the earth back, the earth pushes you forward with an equal force. That's how we move. Sir Isaac Newton discovered that forces never act alone. They always come in pairs. He stated that for every action, there is always an equal and opposite reaction. Look at nature. When a bird flies, it pushes the air downward with its powerful wings. The air pushes back with an equal force, lifting the bird high into the sky. Even underwater, the law holds true. A fish pushes the water backward with its tail, and the water pushes the fish forward. Action and reaction, perfectly balanced. Consider rowing a boat. To move across the lake, you pull the oars through the water. You are pushing the water back, so the water pushes the boat forward. Ever noticed a rotating garden sprinkler? It spins because of action and reaction too. As the water jets shoot out one way, they push the sprinkler head in the opposite direction. Safety engineers use this law to design better cars. When two cars collide, the force car A puts on car B is exactly the same as the force car B puts on car A. We also see this in the recoil of a cannon. When the cannonball is blasted forward, the cannon itself is pushed backward. It's the same principle as jumping off that skateboard. Think about dribbling a basketball. You push the ball down toward the ground. The ground pushes back on the ball, sending it right back to your hand. Let's revisit our balloon. When air escapes the nozzle, it blasts out backward. That backward blast creates the reaction force that zooms the balloon forward. This is exactly how rocket engines work, but on an incredible scale. They burn fuel to create high-pressure gas that is blasted downward. The downward push on the gas creates a massive upward push on the rocket. The harder the gas is pushed down, the more thrust is generated to go up. In the vacuum of space, there is no air to push against. So how does it move? The rocket carries its own push. By expelling mass, it generates its own reaction. An astronaut in space uses the same principle with a jetpack to change direction. Even the International Space Station uses tiny pulses of gas to stay in orbit. Gravity also follows this law. Earth pulls on the moon to keep it in orbit, but the moon pulls back on Earth just as hard. We see this every day in the ocean tides. From the steps we take to the orbit of the planets, Newton's third law is everywhere. It reminds us that we are always connected to the world around us through force. Keep asking questions, keep experimenting, and never stop exploring the laws of nature. Follow Learn with Adeesha for more science adventures. See you next time. Goodbye for now, and stay curious.